Okay, this is lesson 7.4, proving trig identities. We're actually going to spend a few days here proving trig identities, and you can treat today as kind of an introduction to trig identities. We did look at trig identities in grade 11, and we're revisiting them now in grade 12. So as a review, what is a trig identity? Well, a trig identity states the equivalence of two trig expressions, and it's written as an equation involving trig ratios. And since you have an equation that is the result of either a definition or a relationship that exists among these trig ratios, it's going to have an infinite number of solutions, which means it'll work for any angle. It's always true. In order to prove an identity, you can verify it by graphing both sides of an equation separately, and the graphs should end up on top of each other, so they should be superimposed on top of each other, which means they are identical. To prove it algebraically, you need to use the following strategies. Treat the left side and the right side separately, and then manipulate one side of the expression into the exact form of the other side. We try not to work with both sides at the same time. We just take one side and turn it into or manipulate it by using identities or equivalent expressions to look like the other side. Sometimes it's not clear which side to use when you're proving a trig identity, and there's no good strategy for picking a side, because really you can prove a trig identity from manipulating either side. Sometimes it's easy to take a complicated side with a bunch of functions and simplify it. Sometimes it's easier to take a single function and expand it and make it bigger. So really, if you are working with one side and you can't get it, you can stop, get a new piece of paper, start from the other side, and see if you can get it to work from the other side. Sometimes when you're working from one side and it doesn't work, and then you work from the other side and it doesn't work, you might come to a point where you see similarity between those two sides, and then you can use that to kind of mesh them together. So again, starting from one side and working your way through and using that similarity to connect the two sides. But working from one side to prove an identity. Once you've manipulated that one side to look like the other side, you have proven the identity. And once you've proven the identity, you can use the QED notation, which means that you have demonstrated that it is true. QED stands for quod erat demonstratum, and it is Latin for which had to be demonstrated. A few strategies that you use when proving trig identities we're going to show in this lesson. Sometimes we're using common denominator, sometimes we're using factoring, sometimes we're just using other identities. And on that note, some of the identities that we're going to use when we prove other trig identities are the ones we've been exploring in this course and in past courses, like the Pythagorean identity. The sine squared x plus cos squared x equals 1. And there's a few variations using the secondary trig functions and tan. 1 plus tan squared x equals secant squared x, and 1 plus cotan x equals cosecant squared x. And you can rearrange these into any form. For example, if you had a term that's just said sine squared x, you could subtract cos squared x from both sides and replace sine squared x with 1 minus cos squared x. So you can use identities or forms of an identity to prove other identities. There's also two quotient identities. There's that tan is sine over cos and cotan is cos over sine, which makes sense because tan and cotan are reciprocals. Cosecant is the reciprocal of sine, secant the reciprocal of cos, cotan the reciprocal of tan. There's also the double angle formulas, which we explored in a lesson, and then the addition and subtraction formulas, which we explored in another lesson. All of these identities listed here, you'll be given on any assessment when you're asked to prove an identity. So that could be the assignment we're going to do in this unit, that could be the test we're going to do, or that could be your final exam. So if I haven't already, ask for that formula sheet, and you can have it and practice with it, and it will look basically just like this piece from this lesson. So let's prove some basic identities. So our first one is sine x times secant x equals tan x. One strategy when you're given a bunch of different trig functions is to turn the trig functions into just sine and cos. Why that's useful is sometimes you can collapse and simplify when you're just writing identities in terms of one or two functions. And the consistent ones to use are sine and cos because everything's related to sine and cos. Tan is sine over cos, secant is 1 over cos, cosecant is 1 over sine. So everything can be written in terms of sine and cos. So it's like common language for proving identities. So in this example, we're going to work from the left side. You could work from the right side, but we're going to work from the left side. And our left side is sine x secant x. And we're going to use the strategy of trying to write everything in terms of sine or cos. So sine is already sine, so we don't have to change anything there. And secant is just the same as 1 over cos. And now we have sine x times 1 over cos x. And if we multiply those two terms together, we end up with just sine x over cos x. Okay, so we use the reciprocal identity on secant to write it in terms of cos. And now we have sine x over cos x, which one of our identities on the first page, the quotient identity, sine x over cos x is just tan x. So what we actually have is tan x. We now have the left side equivalent to our right side. So once we've shown that the left side equals the right side, we can say that we have demonstrated the proof. QED, as it were. So that's one example. Let's try another. We've got tan x cos x over sine x equals 1. So 1 isn't something that we can really start manipulating because there's so many places to go from 1. We could use Pythagorean identity. We could write sine over sine, cos over cos, tan over tan, sine minus sine. There's literally an infinite number of variations on the number 1. So we're going to work with the left side. And we're going to use that same strategy of writing everything in terms of sine and cos. When in doubt, sine and cos. So here we go. Tan, using the quotient identity, is just sine x over cos x. And we're going to multiply that by cos x on the top. And on the bottom we have sine x. Sine x over cos x times cos x. The cos x's will divide away. So we're just left with sine x over sine x. And sine x divided by sine x, those are the same, is 1. Our right side was 1. Therefore, left side equals right side. We have demonstrated the proof. QED. Okay, so that's using basic identities and writing everything in terms of sine or cos to prove a trig identity. Let's try one more. This says prove by adding or subtracting. We're going to manipulate the left side first. So here we go. Our left side is secant x plus sine x. Why did I pick the left side? Honestly, no reason. I'm actually going to show you the proof from the right side as well. So we'll prove it both ways. So you can see that it really doesn't matter what side you pick. We're going to use the strategy of writing everything in terms of sine and cos. How come? Well, the right side is only in terms of sine and cos. The left side has a secant, so let's replace that secant with its reciprocal identity, 1 over cos x. This says prove by adding or subtracting. So what are we adding or subtracting? Well, we're going to add these two terms together, or these two fractions together. How do you add fractions? Well, to add fractions, you need a common denominator. Sine x's denominator is 1. So to make this have a common denominator, we have to change sine into something over cos x. In order to do that, we have to multiply the top and bottom of this fraction by cos x. So sine is really just the same thing as sine x cos x over cos x. And now we have something that we can add because we have a common denominator. We have 1 in the numerator plus sine x cos x over cosine x. And that is our right side. Our right side was 1 plus sine x cosine x over cosine x. So in 2 steps here, by adding fractions, we have demonstrated the proof. What if you chose the other side? Here we go. We're not going to work from the left side, but our left side was secant x plus sine x. From the right side, we have 1 plus sine x cos x over cos x. If you have a single term denominator, or any denominator in fact, you can split the numerator into 2 different fractions. And the way you do that is you take each term in the numerator and give it the denominator, or assign it the denominator and make it its own fraction. So 1 plus sine x cos x has 2 terms, right? So our first term is 1, so our first fraction would just be 1 over cos x. Our second fraction would be sine x cos x over cosine x. And now we can just simplify. Cosine x divided by cosine x is 1, so our second term is just sine x, and 1 over cos x is the definition of secant. So we have secant x plus sine x, and that's our left side. So we have just demonstrated the proof from the other side as well. Okay, so using those 2 strategies, try the 2 practice questions below and check your solutions on the course website. That's part 1 of proving trig identities. We're going to do part 2 as well, so I'll see you next time for part 2.